We don't give Microsoft nearly enough credit. It's a really impressive business model they've built, which is spying, data acquisition and transaction. But look, this has made the obstacle to moving to Linux a lot less towering of an imposition than it might have previously seemed. And it's time to start benchmarking Linux, to start getting some data out there and available for those looking to jump ship off of Windows. Sorry, I'm not trying to flex right now. Let me just hide that off camera. With the unshittification of Windows and the rise of SteamOS, the requests for Linux testing are coming from more than just a few passionate level 1 text viewers.
Thanks, Steve.
It's been a lot of work, but we finally have some Linux benchmarking data for GPUs, specifically on the Bazzite distribution. This took about 3 weeks of nonstop testing, plus about 2 to 3 weeks prior to that of bench setup, research, and what we call bench hygiene, so researching how you maintain a bench through the process of testing. We're still learning for all this, and benchmarking anything to the level of isolation we maintain and sort of require for our tests, it's a lot of work, and it takes a lot of understanding the controls and experience, so you'll kind of have to work with us as we go through these processes, but maybe this is insightful for some of you. The first round of testing has largely been for our own training. That's what we're going to present today. We ran into a lot of bumps in the road and basically plowed through them all, so we'll detail some of those. We're not first-time Linux users, but I mean, for me personally, the last time I daily drove a Linux operating system was probably about 2009 until about maybe 2012 or so. And I haven't done a whole lot with it except for some NAS type stuff since then. We spoke with some of the Bazzite maintainers during this as well, and that was helpful for getting some of the testing controls dialed in and understanding some of the practices and best scenarios we might want to consider for maintaining a clean, comparable benchmark environment between data sets. So let's get into it. We're directly funding our first Linux GPU benchmarks with your help from the GN Store. This content is brought to you by you, our audience. Our brand new Retro IO themed drink coaster packs launched on store.gamersnexus.net and include 4 distinct coasters per pack, all designed by our team in Blender. You can find the link below. The coaster packs include an old school computer case front panel with a floppy disk in the drive slot, a classic colorway game controller, an IBM Model M inspired keyboard numpad, and a GN logo with all the dials and classic PC case ridges and knobs we know from decades past, back before AI and first-party spyware ruined everything. These coaster packs are easily cleaned under running water and have been fine-tuned to balance drinks and cans while making an easy condensation catch. Plus, they just look cool. We launched these alongside our new unhinged Vaporwave Smiley t-shirt, which is brand new and on the store now, featuring a dystopian censored speech box smiley. You'll see this show up in our upcoming investigation into a raid of a private citizen's home in connection with Sega and Nintendo development consoles and cartridges, something we flew to the UK to investigate. That deep dive special report is also supported by our AI Dystopia Report Series fundraiser on the store, including 4 high-value packs of GN Store items and digital rewards, some including the coasters. Head over to store.gamersnexus.net to support our first Linux GPU benchmarking and our investigations all at once. Back to the video. Quick dose of reality first. Linux still isn't for everybody. It's going to depend what you do. Some users who require certain professional applications, for example, may find that you just have to use Windows and there's no other option because the software you use hasn't moved over or it doesn't port cleanly or something like that. That's the case for our own production machines that we use for a lot of the work we do here. So there's systems that we can run Linux on, like things that might only really access web interface software that works basically anywhere, but a lot of the other stuff, it still requires Windows. So that's going to be a limiting factor for a lot of people, but gaming has gotten a lot more compatible on Linux over the last several years specifically, and if you're one of those web application heavy users with gaming, then it might actually be viable for you now, and even for professional users where there's just more compatibility for your software, that may also be the case. So it is not difficult, in the very least, to throw a Linux distribution onto just a spare SSD or something, throw it into a machine, and see how it goes. And if it doesn't work out, you can always go back to your Windows system or dual boot or something like that. And at least it's worth, we think, experimenting with Linux at this point, because I mean, Windows is really getting kind of nasty with the level of spying that it's doing and how invasive it's gotten, and moving away as much as it can from bypasses to things like always online connectivity, which I personally think for an operating system is absolutely horrifying and should not be tolerated or accepted. And this may be a good time to start considering the jump. So anyway, during this process, we had crashes, we had freezes, issues with anti-cheat, some insanely long, like half-hour long shader compilation times. And in spite of all of this, Linux is still working better than it ever has in its history for gaming. And if more users grit their teeth through some of the initial learning pains, we think that might mean that we can kind of escape from some of the Windows issues as a community, and we'd count that as a win. Just know what you're getting into. It does work better than it used to. It's not perfect. Important disclaimer here first is that our level of testing for GPUs and CPUs on Windows is extremely refined and rigid. We've also been highly automated for almost a decade now. We don't talk about that a lot, but that includes capturing images during test passes for things like image quality checks and a whole lot of cool testing automation and data management automation that we don't talk about. It's just something we do, and then we do lots of manual vetting of it, make sure it's all good. We go through and do reruns manually as necessary, and we get it into the charts. This doesn't exist for us in Linux, and to refactor it all for Linux is not a fast task. So for this, we went entirely manual, which is fine, and we still do that for a lot of stuff. It just means two things. One, it's going to take longer to do. That's fine. We can deal with that. Two, the data is not going to be perfectly comparable, but it's not anyway, because you're looking at Linux and Windows. These are different environments. Sometimes the games themselves are built natively for different operating systems, plus potential API changes where you might need to pivot to a different API to run better. There's a lot of problems. You can't even cross-compare because the software that captures the data itself is different. This is something a lot of people forget about. So the point of all this is that we don't want you today to go cross-compare numbers in these charts to numbers in our Windows charts unless it's one we've handpicked to do so, because we know that it is at least somewhat comparable. You really shouldn't be cross-comparing them. People are going to do it anyway, I know, but even the capture software measures frame rate differently, frame time differently between the utilities that exist. And so these are things that cannot be linearly compared. But the point is, we've taken a lot of care to do all this justice. We just want to be fully transparent that Linux is almost by design a less rigid solution than Windows. It can update more frequently, or at least it has more components that update more frequently. And this is something that has more of an impact on testing. Testing is sort of different from a real use in that you need to maintain a specific environment in order to do it properly for comparison. So methodology is important here since it's all new and sensitive to change. The first thing, again, you need to know, don't directly compare with our Windows testing other than what we've compared for you. And secondly, with testing, we have to strike a balance where we want to be thorough, but we also have to be able to complete the test data set in an amount of time where there aren't too many updates to all the different pieces of the software to where it's starting to invalidate things. So that's the struggle. GPUs are the most straightforward hardware category that we test, so we began with our standard GPU test suite on our standard platform. We knew we needed to start with a single distro. The front runners were SteamOS, which we already have experience with on the deck, CachyOS, or Bazzite. SteamOS was our first choice, but it's not officially available for desktop, so that ruled it out for now. CachyOS should have more cutting-edge performance than Bazzite and might be more flexible, but potentially at the cost of some stability. Bazzite is popular. It's built for gaming. Thousands of you requested we test it specifically, and that's the most important part to us. Its developers have made executive decisions that simplify our own choice making, and they've even contacted us. And most of all, Wendell of Level 1 Techs even recommended it as a stable test platform for us to get started with.
The shortest answer I could give you is probably Bazzite. Bazzite is good because it is an immutable distro, and that is important because it is a big philosophical difference in how the system is managed.
A lot of the Linux enthusiast community is used to tuning and tweaking things and finding ways to optimize or min-max stuff or fix problems that arise. This we have to address right away because testing's a little different from use, where we need a test platform that's predictable and is stable, and most importantly, we have to minimize our own judgment calls wherever possible because we don't want something that is open to change because it was a human decision. And as an example of that, if you start to min-max and optimize or fix bugs for how one device runs, now we really need to put that equal level of effort into all of them. And it's just not viable, or we don't have the experience to do it properly. That's the part I'm really more worried about. So that's why for us, testing something closer to usable out-of-box state is going to help railroad us into a fair configuration for all vendors, as we can always fall back on the rigid decision-making where it exists. Now, Bazzite Desktop Edition comes in at two main versions, NVIDIA and non-NVIDIA. just like the S&P 500 at this point. After speaking with both the devs and Wendell of Level 1 Techs, we set up one drive for each. The OS comes fully stocked with drivers and game launchers, so we didn't need to do any significant configuration after installation, which also means that our test benches reflect the default user experience as much as possible. You still have to be careful with cross-contamination, but it's by doing different things. Bazzite is an atomic bootable container image. There's a full explanation on the FAQ page, as well as advantages versus SteamOS. But the bottom line is that you can just grab an image and slap it on your system. Bazzite's goals are stability and compatibility, and recoverability in case those first two don't work out for you. It's intentionally not the highest performance, most bleeding edge OS, but it's a lot lower friction for beginners, and it's a lot less prone to oh shit moments where, I don't know, it turns out that some feature was broken during testing without our knowledge or something. According to Antheus from the Bazzite dev team, he said to us, quote, "We used to include some gaming-oriented kernel optimizations, but as of August, we do not anymore. We found that most of the testing for those changes involved running, for example, Rocket League at 600 Hz while doing something like compiling a kernel. Nobody does that or cares." Just gonna interrupt to say, a bold assumption of the Linux community, we await your comments post-haste. Anyway, other than that, he said, quote, "We found those optimizations could cause a 2 to 30% performance degradation, where the higher end was on Intel CPUs with heterogeneous cores. This actually ended up hurting our reputation, which is very unfortunate because the version of one of the optimizations we used had a bug. Moving forward, we will no longer make these sorts of changes, so performance on Bazzite should mirror Fedora and Arch, but with more stability as we skip minor versions and delay the major a bit," end quote. Now, during the test cycle for Windows, we freeze the updates for the period of that test cycle. It typically takes us about a week. We're pretty good at it now. But even if we want to run that data for longer, we've found through validation, calibration, lots of cross comparison, and update A/B testing over a year even, that a lot of times there's not big differences. It really depends. Sometimes Windows ships a major change, like for CPUs more than GPUs. But for the most part, the data can remain fairly shelf stable, so to speak. In the very least, we can pause the updates for the 1 week we need to test it without major downsides. Now with Linux, there are a lot more layers, and those updates may come at a much faster pace and sometimes asynchronously with each other. Plus our testing is a lot slower. 1, because it's not automated, and 2, because it's just slower. So our instinct is to freeze versions as much as possible without needing to mod things. Linux has a number of pieces of software, though, that regularly update. These include the operating system itself, that's Bazzite here, the games, which get potentially different updates from Windows, Steam, which gets meaningful updates as well for Linux. The Proton translation layer is really important, the drivers, among other things. Freezing some updates but not others. Like if there's something we just miss, we don't know it exists, and we don't freeze it as a result, that could lead to issues where things break for testing or for a particular device, but not for an end user. Our compromise has been to freeze Bazzite, including drivers, and Proton during the test cycle only, and take detailed notes on everything else, including all version numbers for everything we know about. In the future, we may shift to GOG, which allows using specific game versions. In general, we've accepted that we'll have to throw away more data and start from scratch more often on Linux. We don't talk about the business side of running the benchmarks on the channel too much here. I think it's maybe helpful context for this one. So for us, typically, we would, if we didn't do it the right way, lose money on a full GPU test suite pass. Meaning, if we took 26 GPUs and we ran them through a new suite of games with new benchmark passes, new data sets, new validation, calibrating everything, all of that. If we did all that and then we published one video at the end of it, which is what we're doing here today for Linux, we would lose money. It would not be viable. The way it can work, though, for us is because on the business side, we can then append to that data set. So if we run 26 GPUs in December, and then in January, we want to review the RTX 5090, the 5080, the 5070, whatever. We can append those one at a time as they come out, and that's where it starts to sort of recoup that cost so that it's viable. That's the boring business side of it. If you want some numbers, for instance, I went and looked it up, 85 hours overhauling our GPU testing suite in December of 2024. That included new games, benchmark validation, calibration, running about 26 GPUs through it, experimenting with new methodologies and getting the plan in place for stuff like animation error metrics, and then working through to eliminate bad data, calculate things like standard deviation, all this stuff you don't really see other than the charts. If we were to then only publish a single video with that 85 hours of work, plus the editing work, plus the camera work, plus whatever my scripting time is, that's not going to be sustainable. But because of the way the data is sort of designed to be shelf stable for a little while, like at least a quarter typically, and we do validate constantly to make sure it's not drifting, that makes it work. With Linux, the problem is that it's not quite as easy to hold it in place. So for that reason, simply rerunning all the tests every time we want to add a device for Linux benchmarking, it's not going to work for us. What we're probably going to need to do, for now at least, until we develop the processes for this to be more shelf stable, is going to be running Linux tests maybe a couple times a year at most for GPUs and collecting all new data as fast as we can in that period. The speed matters because as stuff is updating, other things can break, and we might not know if it's because of the testing or if it's because it actually broke. Anyway, that's sort of some of the boring business side of it. The only reason I'm saying this, it's not because, like, pity us, we have to benchmark video games and it takes a lot of time. It's fine. Like, that's what we do. We like doing it. I'm putting it out there because I just want everyone to be aware that currently our processes for this are not as mature, and it might not be possible to get them to the level that they're at for Windows in the near future for us. And because of that, it makes it difficult to do a lot of these types of tests frequently. Because, I mean, it ate 3 weeks of Mike's time running those benchmarks and working through all the issues. Now, we can speed that up a lot, like by choosing things that don't have bugs, but you get the idea, I think. And we're going to keep working on it. It's going to take us some time to get it optimized. But we hate Windows and Microsoft at the moment for the spyware, so it's worth doing. It's worth the investment. All right, to cover the equivalent settings that we'd change on Windows, we set adaptive sync to never, allowed screen tearing for full screen Windows, and set the power profile to performance. We've had warnings from Wendell and others about kernel spin lock performance loss, the CPU performance governor, and plenty of other Linuxy type things. But the advantage of a plug-and-play OS like Bazzite is that we can just install it and run it. Any issues are a valid part of the experience at that point. Now, there are a lot of ways to fuck this up big time. We think we've protected against them. We'll find out. I'm pretty sure we've done a decent enough job of protecting against them in most of this testing. Is that enough qualifiers for you? Can you tell that we don't have a lot of experience publishing Linux benchmarks? It's a lot different, even though we know how to run benchmarks. So we're starting with our existing GPU suite for the most part, including the same settings we use for Windows wherever possible. They're not always all there. We're going to limit the amount of Linux and Windows comparisons. The frame rate data is collected differently. It is Mango HUD we're using for Linux versus PresentMon for Windows. And that feels alone like an apples to oranges comparison, both because of the difference in tools and the difference in platforms. I think a lot of people want them to be compared directly, but really what we care about is just simply how do the GPUs perform if you're using Linux as your OS, so that you can choose between one GPU and the other, just like you do with Windows. How Linux handles frames specifically is a little different. For example, we always allow screen tearing, but the concept of tearing is still new to Wayland. The scope of our GPU test suite doesn't include extended stability testing. We'll report any crashes or incompatibilities that we encounter, but we're not going to validate that Dragon's Dogma 2 can run for 5 hours straight on Linux without crashing. So be aware there may be issues beyond what we're reporting here. Our focus today is on numbers, not stability. We're going to go through the numbers. We have some more critical methodology discussion and issues we've run into to get into. I'm gonna put that after the charts because I know people are skipping to the charts. I just asked that if you are gonna go post this stuff on Reddit or something, to please watch the parts explaining some of the limitations, the disclaimers, the issues, things like that, to have a fuller picture than just the numbers. One other thing, we're only testing some of the most modern cards today. There's a lot of reasons for that. The main one is that it sometimes requires different OS builds entirely, and we're trying to limit how many times we're rebuilding the OS and the test platform because it's a huge time sink. So we're going to focus on the 50 series and on things that are compatible with the builds that we have. We'll worry about going back for other stuff later. And again, do not cross-compare it to our Windows data because it is not necessarily tested the same way. It could even be a different API entirely. So that's all important stuff. Let's get into the numbers, then we'll address the issues during testing. For the GPUs on the charts that have various VRAM capacities, we used 8 GB for the RX 9060 XT and 16 GB for the RTX 5060 Ti. The only reason for this discrepancy is simply due to GPU availability as we managed multiple other tests during all of this, and we'll continue to look at adding more of these if we do another round of Linux testing. But for now, we'll start with these. We'll start with the Windows build of Dragon's Dogma 2 at 1080p max settings. For this testing, we used KDE Plasma 6.4.4, KDE Framework 6.17.0, Qt 6.9.2, Wayland, and 10.0-2E Proton, with the exception of the 9070 XT and the 5070 Ti, which ran earlier in the test sequence and were both experimental 10.0- 2025, September 19. We've got a bunch of other notes as well, but we're not going to run them through them all today. The 5090 leads the chart for 1080p at 176 FPS average. Just like with Windows, we'll need to look at higher resolutions to ensure it's not CPU bound. The 9070 XT is disturbingly close to NVIDIA though, for NVIDIA at least, up at 140 FPS average and leading the RTX 5080's at 134 FPS result by 3.9%. Lows are about the same between them. The 5070 Ti suffers somewhat in 0.1% lows. On inspection, it had one pass with a 23 FPS, 0.1% low, one with 61, and two at 96 to 97 FPS. These are averages, by the way. So the GPU experienced more variance than typical. The 9070 is about tied with the 5070 Ti, but had superior lows. The 9070 also leads the 5070 by 20%. The 9060 XT outdoes the 5060, but the 5060 Ti 16GB outdoes both. 1440p had the 5090 at 154 FPS average, leading the 5080 by 37%. The 9070 XT runs at about the same level of performance as the RTX 5080, which is another good position for AMD, despite seeing a decrease in its relative rank from 1080p. The 5070 Ti trails this, with lows proportionally scaling. Current Newegg prices have the 5070 Ti at $730 to $750 or so. That's going to change probably by the time this goes up, but that's the range it is right now, with the 9070 XT at $600 to $650. In this situation, the 9070 XT is improved on the 5070 Ti in both performance and price. As for the 9070, which is around $550 to $570 on Newegg as we write this, it's outdoing the $500 RTX 5070 by 19%. The 5060 8GB falls off an absolute fucking cliff here and becomes unplayable. 4K draws the numbers down. The RTX 5090 now has a 44% lead over the 5080 as compared to 37% at 1440p, while the 5070 Ti is roughly tied with the 9070 XT. The 9070 is just behind the 9070 XT, which improves on the non-XT by only about 10%. The 5070 ends up below the 9070 with the 9060 XT at the bottom of the chart. The 5060 was not capable of running this test. Black Myth Wukong is next. In Windows, this game heavily slants in favor of NVIDIA with ray tracing enabled. It's more balanced in rasterization, which is what we'll look at first, but NVIDIA is still generally a strong performer here for Windows. In Linux, and at 1080p with this chart, the RTX 5090 runs at 115 FPS average, but it has extremely disproportionate lows that slam its 1% and 0.1% averages through the floor. These aren't anywhere close to the actual average FPS, indicating a bad experience despite a high average frame rate. We'll look at that in a frame interval plot in a moment. Unfortunately, animation error metrics don't yet work in Linux software that we're aware of, or at least not in the same way they do in Windows with PresentMon, so we can't evaluate that part right now, but we can still look at the frame-to-frame intervals. The 9070 XT has a lower average frame rate, but offers a significantly better experience than NVIDIA's flagship RTX 5090. The 5090 has an average that's 9% ahead of the 9070 XT. Not that much, yet the frame time pacing on the 9070 XT breaks away, and also explains why the average isn't much more ahead. The 9070 non-XT repeats this. It's only about a 5 FPS difference in average from the XT and still retains better interval pacing than a 5090. The 5080 follows the 5090's behavioral patterns, as does the 5070 Ti, the 5070, the 5060 Ti, and the 5060. This is just an NVIDIA problem with this combination of game, driver, and operating system. Even the RX 9060 XT is a better experience than the 5090, as its lows are more proportional to the average. For that matter, Intel's B580 is more consistent. NVIDIA has issues with its flagship title with this combination of software. And for 1% and 0.1% lows, it's not just about the absolute number that they are, but how close that number is to the average frame rate. That's what we mean by consistency. Here's a plot of the frame-to-frame intervals, previously known as frame times. We've been fine-tuning some of the language on this since our animation error white paper we released. The frame-to-frame interval in milliseconds for the RTX 5090 illustrates frequent spikes to 18 to 20 milliseconds, up from a typical result of 8 milliseconds. That's a 10 to 11 millisecond excursion frame to frame, and it's frequent, meaning that you can perceive a slight stutter. This is an instance where we'd love to have an animation error metric in Linux, because it'd be a perfect way to drill down into the issue further. For a 5090, this experience is unacceptable. We know it doesn't do this in Windows, so this is unique to the situation. The RX 9070 XT plots with extremely consistent frame-to-frame intervals, with almost no excursions. The few that do exist are no more than 3 to 4 milliseconds from frame N-1, or the prior frame. So while the 9070 XT has overall lower frame rate average or higher frame interval timing, the experience is far better when using it. At 1440p, the RTX 5090 establishes more distance in average frame rate from the RX 9070 XT, yet still suffers from dismal 1% and 0.1% low averages. The end result is that the 9070 XT has remarkably consistent frame-to-frame pacing, with some of the best proportionality we've seen on these charts so far, while the RTX 5090 Founders Edition flounders its way through pacing. The 9070 XT is superior in this test. That may change if NVIDIA is able to fix whatever the problem is. However, a fix would likely reduce the average frame rate by pacing the frames more evenly. 5090 lows here are inconsistent, meaning that they vary widely run to run. The other NVIDIA devices suffer a similar fate, like the 5080. The 9070 ends up better than the 5080 by experience, and is functionally tied in average frame rate. The lows on the 5060 are more even with its average, as we appear to be hitting some kind of floor for the driver. For its price, the B580 is doing well as compared to the 9060 XT and the RTX 5060. Here's the frame pacing for the 1440p results. The 5090 shows the same behavior as before, just with a higher baseline time required at closer to 10 to 11 milliseconds. The excursions adjust accordingly, now at 19 to 22 milliseconds for the spikes, or a deviation of about 10 to 12 milliseconds frame to frame in some cases. The rapid succession of these spikes is what makes the experience bad for the player, at least in terms of how it actually feels to play the game. The 9070 XT looks about the same as before. The average time is a little longer, but the fluidity is far better. Here's the 4K bar chart. The 5090 handles 4K better than anything else, so we finally found a situation where the game load crushes the other cards enough that even an inefficient and poorly running 5090 can still outmatch them. The lows come up a little from the prior chart, mostly because the inconsistency run-to-run is just so high for the 5090's low-end average performance, which is just the nature of poorly paced frame intervals in general. The RX 9070 XT now falls technically behind the 5080 in average FPS, with its lows still better than the 5080, but worse than the 5090. That said, they're more proportional to the 9070 XT's average, so they may still feel more fluid despite being overall lower frame rate. Resident Evil 4 is up next. We had to prune more outlier test passes for this one than other games just due to run-to-run consistency issues. At 1080p, the 5090 leads at 360 FPS average, about 27% over the 5080. We need to see higher resolutions for scaling away from CPU limitations. The 5080 and 9070 XT are clearly unconstrained by the CPU though, and the 5090 makes that much obvious. The 9070 XT is just behind the 5080 in all three metrics, giving the 5080 a 7.8% advantage in average frame rate. Broadly speaking, this isn't looking as favorable for NVIDIA as an Windows environment. AMD seems disproportionately favored here as compared to typically. To be that close to a 5080 is not a good thing for NVIDIA. The 9060 XT is about 48% ahead of the B580 as a result. The 9060 XT is similar to the 5060 for performance. As an aside, the 0.1% low standard deviation is very high in this test overall, although the average frame rate was generally remarkably consistent. At 1440p, the 5090 drops to 316 FPS average and now leads the 5080 by 51%. That's a huge gain over the 27% previously, and is mostly thanks to imposing more of a GPU bind. The 5070 Ti and 9070 XT are about tied with each other, but the 5070 Ti has lower 0.1% low marks due to a lower performance pass. This is real data though, and is representative of the experience, so we've included it. The B580 and B570 don't perform well, again, falling below the RTX 5060 and landing at the bottom of the chart. The cards are cheaper than everything else here, assuming MSRP, so it's somewhat expected. In the very least though, Intel's Frametime pacing performance is good here, with some of the most consistent frame-to-frame intervals on the chart. At 4K, the RTX 5090 now clears a ridiculous 66% lead over the RTX 5080, seemingly continuing to gain as load increases. It's able to brute force its way to the top of other charts. Standouts include the RTX 5060, which actually did okay for average frame rate at 4K, if not for the awful 1% and 0.1% load metrics, which call our attention to bad frame-to-frame interval pacing. The B580 and B570 are at the bottom again, but to their credit, are both better than the NVIDIA RTX 5060 result. The middle of the chart sees the 5070 and 9070 about 10 FPS apart in averages. Starfield is up next. No one plays this game, so we figured we'd multiply 0 by 0 and test it in Linux. The 9070 XT did phenomenally here by comparison to the 5090. Actually, NVIDIA is just straight up screwed in this game, with bad performance as a result of the drivers of the game interaction. Obviously, a 5090 is just better than a 9070 XT in basically literally every possible metric objectively. However, in actual use in this test, its performance is worse than an RX 9070 and an RX 9070 XT alike. The 5090 is just 19% ahead of the 5080 here, with the 5070 Ti about the same as the 5080 and the 5070 not far behind. This is a clear indication that something is just broken in this chain of drivers somewhere and software, and it's falling on NVIDIA. The game was overall extremely consistent in its average and 1% lows, And AMD comes away looking good here overall and has thus far held more of an advantage in Linux benchmarking as compared to its relative positioning in Windows. In Starfield at 1440p, the same situation unfolds. The 9070 XT leads the charts, followed closely by the 9070 non-XT. These two cards remain as close as ever to each other. The 5090 is next, then the 5080. This time, the 5090 leads the 5080 by 24%. That's not normal, but it's at least better. Broadly speaking, NVIDIA is getting wrecked here. It's not even close. The NVIDIA GPUs still hierarchically line up against each other by name, but do not land where expected by actual performance differences. At 4K, the situation improves slightly for the 5090, but not in a way that matters much. The 9070 XT is still in front, now at 60 FPS average, and still with lows that scale as expected. The 5090 trails, basically tying the 9070 XT here. The lows difference is within variance of the XT. The 9070 flanks the 5090 on the other side, so overall, the higher resolution has created a scenario where it's clawing itself ahead, the 5090 that is, but still not by an amount that you'd come to expect from the hardware it has. This looks like how Intel GPUs sometimes feel on Windows. The hardware is clearly capable of more, but it can't break out of some external box. Speaking of Intel, it's not present here because it's just broken in this title. We'll look at that more in a few minutes. Dying Light 2 is next, first at 1080p. The RTX 5090 leads everything here for average frame rate, including about 43% lead over the 5080. The lows for the 5090 and 5080 illustrate a limit to how close they can get to the average of NVIDIA's higher-end devices, where we're bouncing off of some kind of driver or softer ceiling. The 9070 XT and 9070 both carry lows closer to the average, once again, with average results for the 9070 XT about tied with the 5070 Ti, but better 1% and 0.1% low averages. The B580 appears at 74 FPS average, showing that it's playable and competitive with at least the 9060 XT. Have we said average enough in the last two paragraphs? I thought so. Let's move on. One thing here, the RTX 5070 Ti had extremely high run-to-run variance that appears to be just a part of the performance characteristics for this configuration. We didn't see this with all of their devices. Normally, what we would do is, because we have enough data to support it, we'd strip out the bad results, rerun it all, and see if they repeat. And if they don't, we call it some kind of test deviation or an issue of that specific run, like a Windows background task. In this case, we're including the data because we're still new to Linux testing. This appears to be a real result, not some test outlier. This plot shows that overall, the frame-to-frame pacing of 4 passes is generally inconsistent. The spikes you're seeing above each cluster of data are undesirable, but the worst one clearly happened just before frame 3000, where we had a spike to about 46 milliseconds. This is long enough that you definitely notice, even though it is a single spike. The 1440p results have the 5090 50% ahead of the 5080 in average frame rate, with the 5080 leading a nearly tied pairing of 9070 XT and RTX 5070 Ti. The 9070 XT maintains better frame interval pacing, although not by as much as some previous results. The RX 9070 is likewise consistent. The B570 ran at 43 FPS average and is plotted here as well. At 4K, the RTX 5090 held a 119 FPS average and lows that were still disproportionately low as compared to those of the 5080. To us, this indicates again that there's a ceiling the higher performance NVIDIA card is bouncing off of for pacing. The 9070 XT ran at 64 FPS average, roughly tying the 5070 Ti and landing within error of its 0.1% lows. Predictably, the 9060 XT, 5060, B580, and B570 can't really run this test. It's okay though, we still included the data just in case the scaling is useful. Cyberpunk 2077 Phantom Liberty's up now, first rasterized. Immediately the first thing we observed was the higher standard deviation of this test, with 0.1% low standard deviation about 10 to 11 FPS, which is the highest of these charts so far. At least 3 cards are in this range for this test. The game is just more variable than in our Windows environment. The RTX 5090 ran at 195 FPS average, leading the 9070 XT by 32% in average frame rate. However, the 9070 XT again has superior lows to the NVIDIA RTX 5090, and in a big way. Fortunately for NVIDIA, the card is still overall playable and the large spikes aren't easily noticeable. Because its lows are high enough overall, it may be the case that the 5090 maintains a better experience, but only by brute force. The 5080 trails the 9070 XT for average frame rate and significantly in low averages. The 9070 is close in average FPS to the 5080 and advantaged in lows. Intel's B580 ran at about 60 FPS average, which isn't bad for an ARC card in this game. That has it behind the 5060, which leads by a 20% in average frame rate. But they are roughly tied in 1% and 0.1% lows. At 1440p, the 5090 held a 148 FPS average with lows at 104 and 90. This is a 46 to 50% lead over the 9070 XT and RTX 5080, which have about the same average frame rate. Lows are also numerically better, but they are less proportionally spaced from the average. The Intel B580 drops to 40 FPS due to the heavy load of 1440p, following the RTX 5060. The 5060 struggles with the combination of VRAM limitations and NVIDIA software-specific issues in the this test on this OS. We don't expect the 5060 to be able to play this game at 4K, to be clear, but other than this result, the rest is similar to what we've seen previously. NVIDIA's results are improving at the low end, but are still disproportionate in the 5090 as compared to the other devices. The 9070 XT struggled at 4K, landing at 48 FPS average and trailing the 5080 in all three metrics. The B580 and B570 both massively outperform the 5060, as does the 9060 XT, particularly in the low metrics. We're getting into Baldur's Gate 3 benchmarking now. This game is different from many of the others here. It has a Linux native build and a Windows build, and its test matrix gets more complex by the fact that it has Vulkan and DX11. The Linux native build had some serious issues that we'll talk about in a few minutes, but we still tested it at 1080p with the Linux native build running the Vulkan API. NVIDIA runs completely sporadically and unreliably. We are well aware that the 5090 is below the 5070, and that obviously is not how these cards should behave, nor does it seem like a normal or good test result. But after retests and evaluation, the only thing consistent is inconsistency when it comes to NVIDIA with the Linux native build of Baldur's Gate 3 with Vulkan. The 9070 XT ran at 238 FPS average here. Its lows weren't proportional to that average and are overall less consistent than we'd like and than we saw in other games. The 9060 XT lands predictably below that, followed by a host of unreliable NVIDIA results. Now, the tests, again, produced these numbers, and it is what happened, but it's clearly just broken. Broadly speaking, the build is buggy. Due to issues with reliability, we're not listing error bars on this one. 1440p is also messed up, as you'd expect. The results for NVIDIA are, again, unreliable and all over the place. It's clearly just straight up broken. The 9070 XT isn't as consistent as it should be, though at least runs at an average frame rate that's okay. Let's move on to a different build. With the Windows build and Bazzite running DX11, things look more normal. The RTX 5090, the 5080, the 5070 are bottlenecked on CPU performance, with the 5060 Ti also bottlenecking but not as hard. The 8GB RX 9060 XT ran at 130 FPS average and had lows similar to the RTX 5060 8GB card, both significantly ahead of the Intel B580. Even still, Intel manages 79 FPS for the average and overall okay lows when considering its generally disadvantaged position. The B570 isn't far behind and matches the scaling we'd expect from prior Windows scaling comparisons of the two Intel models. At 1440p, things are the same, just scaled down. The top three cards are hitting a CPU or other bottleneck, with the 5060 Ti occasionally bouncing off of it, but still somewhat struggling on its own. At 4K, the 5090 hit 170 FPS average, which is technically ahead of its 1440p result. That'd make no sense in a GPU bound scenario when going from 1440p to 4K, but in this case, the results at 1080p, 1440p, and 4K are all bottlenecked on non-GPU components for the RTX 5090, possibly also including software. The end result is that the results will be slightly more variable due to different constraints. Effectively, all three resolutions are identical for the 5090 because of external limits. We were able to get the 9070 XT to run in this one. Its result was 103 FPS average, whereas we saw 115 with the Linux build and Vulkan, although not directly comparable. Moving on to ray tracing benchmarks, starting with Cyberpunk 2077 at 1080p, NVIDIA has always had an advantage in this test on Windows, and that sustains here. A lot of that is just from the actual hardware itself. They're just better with their RT hardware right now. The 5090 held a 135 FPS average, leading the 5080 by 46%. The 5070 Ti follows, with the 9070 XT showing up at 72 FPS average and landing between the 5070 and 5070 Ti. Intel's B580 actually did well here with its 58 FPS average, planting it just ahead of the 5060 Ti. That's a compelling argument for Intel in this specific case. The RTX 5060 fails completely and cannot run this test. 1440p is predictably heavy for these cards. The 5080 is the last card to technically perform above 60 FPS average, with the 9070 XT approaching the 5070 Ti but not meeting it. In this situation, AMD does not have an advantage in low performance and is not more consistent in frame pacing than NVIDIA. Intel, however, is disproportionately good for the value of its hardware and approaches the RTX 5070 while maintaining roughly equal or slightly better lows. 4K is too heavy for this configuration of these cards, but we still ran it. The 5090 maintains actually good frame interval pacing here, with its lows relatively close to its average, but still it's at 49 FPS average. The next closest card is the 5080, and that's only at 30 FPS average. We'll just do these last two RT charts. In Black Myth with RT Medium and FSR Quality, the 5090 ran at 113 FPS average, leading the 5080 by just 30% and roughly tying in lows. AMD's first appearance isn't until below the 5060, and even then, its low performance is disproportionately bad. In this situation, AMD is getting comparatively crushed. Overall, this is something of a reversal from prior charts. AMD has disproportionately bad lows and overall performance. NVIDIA, meanwhile, outdoes it. The RTX 5060 struggles in average frame rate, but did okay in its lows. It seems to float closer to whatever barrier exists in these scenarios. Dying Light 2 is next, with ray tracing now. In this test, NVIDIA again outperforms AMD significantly. The RTX 5070 outdoes the 9070 XT here, with only the 5060 Ti and 5060 behind the 9070 non-XT. Overall, on high-end hardware, most of the games we tested ran without any major issues on Bazzite here. The Linux gaming environment is changing actually every day in a lot of cases, and so any individual bug we experienced could be already gone, it could be gone tomorrow, and Intel cards and cards with less VRAM in particular, like the RTX 5060, seems to be more likely to have problems in testing. Before running the test, we were having a hard time determining whether people consider NVIDIA's Linux support to be bad in the sense that the cards don't work, or bad in the sense that people don't agree with NVIDIA's approach and think it doesn't align with the spirit of Linux. So from Antheus again, quote, in the context of NVIDIA drivers, open refers to the kernel module, which is now under the MIT license, but the drivers are still proprietary. Before the open module, there was a closed module, and the main difference between them is that the closed module was made for pre-GSP or GPU system processor cards. Before GSP, the NVIDIA driver did a lot of heavy lifting and had, for example, 10,000 lines of monitor EDID fixes. Stuff like this is important proprietary information for them, so the driver was closed source, which made a lot of Linux users upset and was a legal gray area with the kernel code. Now, with GSP, which is a coprocessor on the card, they can shove all those fixes in the firmware of that coprocessor, which is closed source, and distribute an open driver that communicates with that. It's just fancy software engineer lawyering, end quote. For gaming, the NVIDIA Bazzite build worked as well as the non-NVIDIA build, at least with the relatively new GPUs we tested. Now, I will say, for Patrick and myself, it was an awesome change of pace to be directly contacted by the developers of Bazzite, Mango HUD, and pretty much any open source tool that we mentioned publicly in the course of working on this. On Windows, the OS and the driver are out of our hands, and Microsoft employees only talk to us on strict conditions of anonymity. So it's a pretty big change, and on Linux, being able to directly ask for information and request important features and updates, that's pretty cool, and it's a great sign. Now, keeping it real with everyone, it's not perfect, and you need to set your expectations. It's still worth trying though, but here's some of the issues we ran into. We can thank the Steam Deck for normalizing how well so many games run through Proton. Although we had issues in some instances, it's still largely true that it's just a lot better than it used to be. As Steam Deck users are aware, some anti-cheat software flat out refuses to run, which means the games can refuse to run. We dropped F124 immediately for this reason. This is the only game from our suite that was affected by this, but since anti-cheat is usually associated with popular mainstream games, this remains one of the most significant obstacles to Linux gaming. Our two RE Engine games, Resident Evil 4 and Dragon's Dogma 2, didn't show any options for ray tracing. It's a known issue, and it may be possible to work around, but not without a level of tweaking that we're trying to avoid for purposes of maintaining a sterile test environment. We're skipping RT tests for these two games on Linux until Capcom figures it out. A few Steam games have native Linux branches, which Steam always prioritizes for download on Linux. Unfortunately, sometimes the native Linux versions suck, not necessarily for any reason other than the developers decided to make them that way. In the case of Total War Warhammer 3, the Linux build lags significantly behind the Windows version. It looks like most users opt to run the Windows build through Proton instead, so that's what we ended up testing. Baldur's Gate 3 is another game in our suite with a native Linux version, although it only came out after we had already started testing, and it promptly broke desktop Linux installs because Larian forgot about non-Steam Deck Linux users. This distributor-side messiness will become more common as the Steam ecosystem expands. We also found that the full screen mode in Baldur's Gate 3 would always run at the native display resolution regardless of in-game settings, specifically with the Linux build. With Cyberpunk 2077, with our RT medium settings profile applied, we'd consistently get crashes on the second loading screen, specifically the second one. We could load a save once, but trying to reload or exit to the menu would crash the game pretty much every time. With our non-RT settings profile applied, this didn't happen. We also had issues across multiple games that may have been caused by low VRAM. For example, the RTX 5060 was able to struggle through Total War Warhammer 3 testing at 1080p. But it completely failed to get past the benchmark loading screen at any higher resolution. Intel's cards had the most problems in general, although we were told by Bazzite's developers that Intel GPUs would be the most affected by updates. So, pausing updates may have prevented some fixes, but that's the trade-off we have to make. They were only paused for a couple weeks here. Using the B580, the native Linux version of Baldur's Gate 3 wouldn't launch. Dragon's Dogma 2 couldn't run long enough to be benchmarked, and Starfield couldn't load saves. And if Starfield can't load something, that's really saying something. We also saw flickering and artifacts at desktop. None of the games in our test suite showed RT as an option with Intel, except Cyberpunk 2077, and when we moved down to the B570, it couldn't even run Cyberpunk with RT without crashing. Now, to be fair, Cyberpunk with RT crashed consistently on the RX 9060 XT as well, but Intel has some special considerations here. We also had multiple issues that may have been related to Mango HUD, which is part of the logging software. The most obvious was that games would frequently crash to desktop when Mango HUD finished logging. We've been in contact with Mango HUD's developer and have some ideas, but for now, we're just sort of dealing with it. We also had games freeze for up to a minute at a time, which could be worked around by tabbing out and tabbing back in. We intentionally hid the Mango HUD overlay during all the testing because of an earlier issue on the Steam Deck where any overlays would cause stuttering and other issues. After a certain point, Mango HUD stopped working with the Heroic Games launcher, which we were using to run Cyberpunk 2077. This was alarming mainly because it implied that something was updating outside of our controls, despite being so explicitly careful and controlled with all the software versions. Although it may have been due to Free Desktop's policy of marking releases EOL after 2 years. Someone on Reddit had a related problem that pointed us to a fix, and then they deleted the post, so good luck. Steam's first-time shader compilation step took an extremely long time, especially with NVIDIA cards, up to 25 minutes for Starfield, for example, on one of the NVIDIA cards we tested. Many of the Steam games we tested forced tiny shader cache updates every day, which is behavior we've seen on the Steam Deck as well. So overall, we've got some initial numbers. Now for us, this was mostly exploratory today, and the biggest thing we've learned is that this is going to be difficult to get to the level we're at on Windows where we can just append a card in, say, a month or 2 months later after collecting the core data set, because it changes a lot more. Now, there's another compromise we haven't talked about here, which is because I don't really like it, but another option would be to allow the updates to keep going, catalog them in some way that's transparent, like whatever next to the card or something, so if Proton changes or something, and then run it anyway. But now you're cross-comparing new data to old data, and if the percent difference swings as a result of that, but you haven't retested the old stuff, then it's not accounted for, and it makes the new test look potentially unfairly good or bad performing, depending on how the update went. So anyway, there's stuff we could do to further improve this. An example would be hand-picking games that specifically run well on Linux, regardless of any other usefulness, like comparing to other data, stuff like that. That might help speed things up a lot. There's other stuff we could do too. We can maybe port some automation, whatever. So we have ideas we could do, but in the very least, we got it started. This has been a huge community request for a very long time. I wanted to give some context for like why this isn't easy to just roll out and why it's not quick for us. You could do it quicker, but we really have rigid processes to try our best to maintain data integrity, and for something we're less familiar with, that takes a lot longer. So hopefully it's interesting to you, and depending on how the performance does and everything, we'll look at doing these more frequently. We can't do them as frequently as Windows benchmarks for GPUs yet. But who knows, it may get there. Thanks for watching. If you want to support this stuff directly, because we could really use your help on something like this. This is like, it's a lot of effort. I'm not going to be able to just add a GPU to the chart like I was really hoping I'd be able to do. It's just, it's going to be a disservice if we do it that way without it all being really packed in. So if you want to help us, go to store.gamersnexus.net and you can grab something like our new Retro IO themed coaster packs or our backer tiers for our AI dystopia series of special reports that we're working on right now, and that'll help us out a lot, while you get something cool in return. For example, our new unhinged vaporwave smiley t-shirts with the censored speech box, or our YouTube copyright strike takedown t-shirt, which we dedicate to our good friends at Bloomberg. Thanks for watching. Subscribe for more. We'll see you all next time.